Hello, everyone. Thank you for joining today's DoD Environmental Planning and Conservation webinar series presentation. As a reminder, today's presentation will be recorded and then posted on the Natural Resources Denix website under the Resources tab. Today's presenter is Eric Britzke, Research Wildlife Biologist with ERDC, the U.S. Army Engineer Research and Development Center. He will be discussing acoustic surveys for bats, detector placement, call analysis, and interpretation. Following the presentation, we will have time for questions. Before we get started, please take a moment to make sure your phones and web browsers are on mute. With that, I will turn it over to Eric.
Thank you, Daniel. So the presentation I'm going to give today is a continuation of a webinar that was presented last week that talked about the basics of echolocation and bat detectors. And so today we're going to focus really on the deployment of the detectors and give some advice on proper placement. We're going to talk about call analysis and interpretation. And if any of you know me, you know that I can talk for an extended period of time on call analysis and interpretation. I'm going to try and keep it short and give plenty of time for questions. And so when we talk about just general bat detector deployment guidance, there's some general patterns we talk about. We think about deploying detectors in places where we have high bat activity. We tend to try and concentrate and determine what species are present in an area. And so we want to kind of get the most bang for our buck and put those in high concentration areas. And so those may be water sources, edges, linear corridors, all that kind of stuff. And so the other thing that's important about bat detectors is that we can deploy them in places that mist netting wouldn't be very effective. And so this linear corridor here, you can actually see the mist net story across it. I believe this is at Fort Drum. And so sometimes you can sample the same places, but other times, like the water sources here or the field edge, are very difficult to sample. And so bat detectors have that advantage of being able to sample bats in a wide variety of habitats. And so we try and put those bat detectors and deploy them in places that optimize the detection of bats. And so we've got some, I've got some guidance here. The biggest thing, and we talked about this last week too, is each kind of microphone that you have, whether it's a directional or a hemispherical or an omnidirectional microphone, has kind of a zone of detection around it, in which case if a bat flies through that area, it's going to be detected. And so what's important is to try and maximize the amount of time that bat is spending in the detection cone. And so, for example, if you have a linear corridor, you'd want to put a directional microphone so it's pointed down that linear corridor. And so that maximizes the length of the call and the quality of the call recorded. So that's one of the options with a directional mic. With an omnidirectional or hemispherical, you need to try and deploy those more in the middle of the linear corridor and get them out so that you can maximize the time that they spend out. What you want to think about when you talk about detector deployment is making sure that the area that the microphone is sampling flight available space. And so you don't want to kind of waste it by putting a bat detector or a microphone on the edge of the habitat if you had omnidirectional, because you'd be kind of reducing the detection cone substantially there. So again, trying to maximize the time the bat spends in that detection cone as much as possible. So linear landscapes are very easy. Non-linear landscape features, we're talking about forests, openings, large lakes, all that kind of stuff. And so with those, we kind of can get away with, because bats aren't necessarily focused in a certain flight path, we can talk about putting them so that we reduce the amount of clutter within the detection cone. And so deploying them on a, like we talked about last week, deploying them on a pole to elevate the omnidirectional and the hemispherical, to get them above ground level are good factors there. And so another thing we want to do to improve call quality, and that's what all of this detector placement is it's trying to maximize the call quality that we can obtain, because that just makes the analysis and interpretation that much easier. And so one thing that we can do is we can or minimize the chance of reflection occurring. And this happens when you're near any hard flat surface. This could be not only the kind of artificial things that you're thinking about, a building or a road or something like that, but also nice still water is a great reflector. And so you want to try and minimize the reflection that you're detecting. And so you put your bat detectors in places where you're not pointed straight at that hard surface. So in terms of detector deployment, directional microphones, because they have a long distance that they can detect a bat from a microphone, they're typically deployed on or near the ground, and so it's in some ways it's easier to deploy them. The other types of detectors or the other types of microphones, the omnidirectional and hemispherical, like I said, tend to be put up on poles or in trees, factors that get them up in the detection or in the proper detection cone. And as I said a couple times, and it's worth saying again, it's really the net result of all of this is try and maximize the call length. With that, you tend to get a higher quality call, and then that obviously makes the analysis much easier. And so as you're deploying these detectors, think about that detection cone and think about how to maximize the time the bats spend in that detection cone. So when we talk about acoustic sampling, there's basically two types of sampling. Most people think about passive sampling, where they just put a bat detector out on the landscape and let it record for a day, 2 days, months, years, but an extended period of time where that bat detector is stationary. This is the type of sampling that's typically done with NA bat. There's a lot of that done. If you are from the Eastern United States, you're familiar with the Fish and Wildlife Service regulatory clearance surveying that that relies on passive sampling. And then when we look at long-term monitoring, obviously that's passive as well. Another thing that's not commonly used as much, but active sampling is really important. And this is when the detector is moved along a predetermined route. Sometimes this may be a walking transect or in a car. There is a part of NA BAT that uses this for population monitoring. And the nice thing about this is allows you to cover a large area and get an idea of where maybe bat activity is highest, so you can concentrate sampling in the future. And so these are two different types of sampling. Here's an example of what we can get from some transect sampling. Again, this provides a snapshot across a broad area. And the nice thing is it allows us to assess the population level impacts to bats, because as we're moving along, in this case, in a car, the number of files we receive for a certain species is an index to the number of the abundance of that species. And so we can determine much finer population level changes that occur using this transect. And so this on the right is just an example. This was collected before white nose, but these are the different colors or different species that were detected. So red is big brown bats, blue or little brown bats, and yellow are, I think, Cory bats in this example. And so what we can see is not only can we get a good picture about what's going on a large scale, but we also have an idea of where there's a peak in activity, and maybe we can concentrate on those peaks. So with fixed point, obviously it allows extensive sampling with very little human input. The way we can do this now with the detectors we have, we can deploy for weeks on just a set of AA batteries or D batteries. If you want to go with a solar panel, then you can go years with that sampling. It really allows us to overcome the impact of temporal variation. So we have differences in activity from night to night. And in some places, we can sample these areas that we can't sample using other techniques, which is nice. On the right is an example for data that I recorded at West Point. And this was obviously sampling during the fall, looking at fall migration. And what we see here is we see two strong peaks at one of our sites, and these are mostly big brown bats. And so we have 2 nights where activity is through the roof. And if we were to miss those 2 nights and say started sampling on 1 September, we'd have a very different picture of what the bat activity looked like here. And so this is the power of looking at this this temporal variation with a fixed point acoustic monitoring. So that's the part for detector deployment. And so now I want to get into the call analysis interpretation. So the steps in the process of trying to identify bats by their echolocation call, the first step is obtaining a known call library. This is obviously required for all species you want to try to identify. But the idea is that you need to be confident of this file was created by this species. And so call libraries can be time consuming to construct, but they're really vital in determining the ability to do identifications. The next step in the process for this is filtering. You have to remove the non-bat signals that were recorded. This may be extraneous noise. This may be situations where it's actually bat calls, but they're low quality call fragments we have to remove. We have to remove things like echoes. And so we have to clean this up so that we're trying to identify those search phase calls that we talked about last week. And then the last step is obviously comparing that with that call library. And that comparison can be either a visual comparison or a statistical comparison. And we'll get more into that later. So collection of a known call library. There's a lot of different ways that can be done, that can be used. Light tagging is the way that I have done the most. This picture on the right shows a small silane light stick on the red bat that's getting ready to be released. And I don't even want to think about how old this picture is. It's fast approaching 30 years old, probably. And so we've been doing this for a while. Obviously, that's why we don't have gloves and stuff like that. The good days when we didn't know about white nose syndrome. Other ways we can do a call library: recording outside a known roost. So if we're careful, we can be selective. We can make that work. We can record at a site just where the ID can be determined. So sometimes we can see a red bat flying in a street light or something like that. And then there's also a zip line technique that works well for some species that will allow them to get known calls. But the idea is we're trying to get a good quality known call library. And so what we typically see is, here's 2 examples of the same species. On the left is a light tagged recording. So we see a nice call sequence. Unfortunately, when we do passive recording, we get lower quality stuff. And so on the right is a passive recorded file created by that same species. And so what we have to do is try and make sure that the identification process we use based on the light tag bats actually translates and applies to these passively recorded call sequences. And that's something that we're working on. So my first statement, if you don't remember anything else, this is the thing to remember so far, is any call ID is only as good as the library in which it's based. If you have a poor quality library, your identification is going to be terrible, and it doesn't have anything to do with the call quality or the methodology used for identifications, anything like that. It all goes back to that call library. And so when we think about factors that may be affecting species ID, we've got the recording environment, and we talked about last week about the potential impact of clutter on calls. We've got the impact of the analysis. Are we filtering correctly? Is our call library suitable? Both of those factors not only interact with each other, but also interact directly to form our acoustic ID process. And so we're trying to improve all of that to maximize the accuracy of our acoustic ID. So filtering is a huge step. So if we try and identify low quality sequences, we're going to have a problem. Here is an example of a zero cross file. We have a bunch of search phase calls here. This is just, and there's also a bunch of extraneous noise here. When we do our filtering, we can have something like this where the gold and the red are noise that are removed, and then we start focusing in on the actual search phase calls are important. And so this is really important, as you can imagine. If you filter too much, you remove too many of the good pulses, and your identification suffers. If you filter too little, you have too much extraneous noise and call fragments in, and you reduce the process then. And so this filtering is really trying to find that sweet spot of not too much and not too little removal. So here's an example. This is old data, but the idea is when we filter, we've got to try and identify some things as not identifiable in the process. And so if we look at the proportion of just sequences that are identifiable, so that survive the filtering process, you can see it varies for different habitat types. And what's important here is not necessarily the specific number. It's that we have some variation across habitat types. And the other thing is we're talking about fewer than 50% of the calls are identifiable. And so that's a really important thing, is we have to be able to say, hey, this call is, we know it's a bat, but it's too low a quality for us to try and identify the species. And so we can just identify as a bat and move on. And that's one of the reasons we do things like high and low frequency classification. So qualitative identification is the process the identification process that started initially. And this is basically just a visual identification. And so you're using things like minimum frequency, the general shape, maybe some parameters that you extract to be able to classify these based on your experience. And so it is just a visual examination. And so on the left is a big brown bat. Its minimum frequency is about 25 kilohertz. In the middle section is a little brown bat. Its minimum frequency is about 40. And so if you just had a situation where those two species were present in your area, then qualitative identification would be quite easy, and we'd be done with this talk and everyone could go enjoy lunch. But the problem is when we get to other species like Indiana bat, where we start having more overlap and the differences become more subtle, it obviously becomes much more difficult to separate these qualitatively and to do it in a repeatable way. And so because of those issues with qualitative ID and the length of time it takes to do the analysis, we really have focused on quantitative identification. And this is basically uses statistical analyses to do this work. So we remove some of the user error and observer bias, and then also make it much faster and easier to do. So why do we do this? We talked about this accuracy. Generally pretty good. Again, there's some things we'll talk about later. Consistency is a big deal. It doesn't matter if you're you're identifying things for the first time, first calls of the year or the last ones. The quantitative methods are very consistent in structure. We have a measurable bias that we can use. So we have some accuracy rates. We can figure out what's going on. They're obviously reproducible. We can run the same files through a program and have the same results. And efficiency is important. We can analyze large number of files very quickly. And so when we do develop a quantitative method, what we do is basically come up with a classification matrix. And so we develop a model, whether that's a discriminant function or a neural net. And then we hold back some of our call library to use for testing. And that's what this is basically we put the test files back into our classification model and say, hey, what did it actually say it was? And so on the left are the actual species IDs, and on the top are the species IDs from the classification model. And so on the diagonal are the correct classification rates. And then we also have the misclassification rates there as well. And so, for example, in the first column, 246 of the files were identified as big brown that were actually big browns. But 7 files were actually identified that 7 files that were big browns were identified as red bats in this example. And so what we have here is the producer's accuracy here is basically the accuracy rate for that species. If we put in files of a species, how likely are they going to be that they're that classification? So not only can we get our overall classification rate, but we can figure out which species are causing problems in this classification. What species overlap with other species, and at what rates they do it. You can see, for example, with red bats, they overlap with multiple species. And so that's important for us to know. Not only that we can identify them accurately 80% of the time, but that there's multiple different overlap and classifications there. So once we get that classification matrix and we get those accuracy rates and the misclassification rates, now the question is, how can we use that information? And so for acoustic identification, sometimes the myotic species can be quite easy to identify if you have good quality files. The biggest problem, obviously, with those is that low quality, and when we have things like noise and call fragments. One thing that I stress in all of these talks is that there's very few distinct species groups. We often hear about a myotis group, and we say, well, we don't know which myotis it is, but we're just going to dump it into that group. I'm a firm believer that there's not a true myotis group, and that's because red bats can look like lots of different species, including lots of different myotis. And so that's the issue there. So I really refrain from using those groups. And then I think as we get more information and we understand more about red bats, we just understand how big a problem they are, because they can overlap with anything. And they're the bane of the existence. If we didn't have red bats, classifications would be much, much easier. Okay, so we looked at the classification rates, and we didn't see 100% accuracy rate. And so the question is, with any one file, we don't really have confidence. We have some confidence that the species ID, but there's still some uncertainty associated with it. So because it's not 100% accurate, how can we interpret presence of a species based on the number of files? And what's important here is, and I do this really quickly, is bats produce an enormous number of search phase calls, about 36,000 actually pulses per hour that they're producing. And so some of those pulses may look like other species or may overlap other species. And so there's an enormous amount of data there that we have to go through, and we need to keep that in mind as we're filtering things out. And so for our acoustic ID results, if the species IDs were 100%, if we were able to do that, and that if we had 9 files identified as species A and 1 file identified as species B, then we say both species are present. Done, no big deal. Unfortunately, this is not the case. And so what we've done is we utilize a method called maximum likelihood estimate, or MLE. You may have heard this. And basically what this does is this is a statistical approach that takes the classification matrix and the expected error rates and correct classification rates from that classification matrix table, along with the number of files identified as each species from a single site night, to come up to test whether all of those files that were identified as a species were misclassified as other species. And so this is really important. I know you guys are really interested in hearing about null hypotheses, but the idea here is if we have a p-value that's very low, then we can't assign, then we can basically determine that species be present on the landscape. And so an example for that is the same example. We had 9 files identified as species A and 1 as species B. But if we had a situation where species A was identified at 90% accuracy and was misclassified 10% of the time, then the interpretation for that would be species A was present and species B was not. And the reason is because it's much more likely that that one file that's identified as species B was actually classified as species A incorrectly. And so that's basically how we use that classification rate above to determine our species presence. So hopefully that helps explain MLE. This is an example. There are different outputs for the different programs, but the idea is for each site night, we have a, in this case, a p-value to determine species presence at a site. So for all 4 nights that were sampled at this site 1, big browns was present at that site. Although on the same 4 nights, the eastern redbat was not detected at any of those 4 sites or 4 nights. And so we can use the results of this to determine species presence out on landscape. And so that's how we interpret the MLE. And that the idea with that MLE is to try and make it easier to comprehend what's going on with our classification rates, our species IDs. So the MLE output, well, the automated analysis output generally has 3 different levels of output. The bottom one is the file level analysis, and this is basically identifying how many pulses were identified as each species for each file. Very detailed level, and it does provide generally the species ID for that individual file. And so that provides a lot of information. There's also a night level summary that summarizes that file level and says, okay, how many files were identified as species A on this site, on this night, how many were identified species B, and so we provide that information. And then the MLE basically uses the night level summary and the classification matrix to come up with determining real presence. And so what's important here is you need to get past the idea of a single file or some pulses being identified as an endangered species as being a relevant metric. It's really about this MLE estimate that determines whether a species is present or not on the landscape. So that with the analysis approaches, qualitative, the pro that it has is it can see the big picture. It can look at kind of the entire file. It can look at what's happening across the night and say, and get a better idea of what species may be there when you're pretty experienced. Cons can be it's very inconsistent. I know when I do qualitative identification, I've been doing it for a long time. I'm really rusty when I start the field season with it, but by the end, at least I think I'm much better. And so I think there's that variation there. We know there's some unmeasured bias. No one is 100% on their classifications there. And so the fact that we haven't measured that really makes it difficult to interpret some stuff for qualitative IDs. And just very inefficient. If you had to look at each file that you recorded over the night of, several detectors over several nights, you would have no other job but to do qualitative ID. So quantitative ID are basically just the reverse. You have consistent, you have measurable bias. They're very efficient. The problem is if we have a call library that's lacking, or we may have some other systemic errors that are present in the program that always lead to a misclassification. And so we can't just take the classifications for the quantitative, the acoustic ID programs and just take them and run, but we need to try and improve those. And that's the main point there. So when we talk about the interpretation of the acoustic analysis, there's a bunch of different options for in terms of methodology. One, you could do qualitative identifications only. You could just look at each individual file. Like I said, very time consuming, but you can do that. You can get a species list and do that. You can do a quantitative only. So the program spits out the answer, you just take the answer and you move forward. Nice, easy to do. It just there may be some issues associated with that. And then the idea that most people do is use qualitative ID to kind of check the quantitative IDs. And I think what's important there is we need to check not only the false positives, which is what we focus on. So say a program said northern longyearbit was present on the landscape. People tend to check that type of file to see if it's maybe a false positive, but we kind of ignore false negatives there. And so if we're really going to do a good job, we need to consider both false positive and negative IDs in that process. And so when we're doing this and we're trying to decide how we want to interpret this, we have to remind ourselves that quality is a spectrum that we're dealing with. And so there's no good point of a break-even point of this is good quality call, this is bad quality call. Instead, it's a continuum, and we need to remember too that the number one source of misidentification is basically trying to identify low quality calls, basically. And so we need to be able to say, hey, I'm not sure what that is. I'm going to say it's a bat, and I'm going to move on. With the idea, remember that I just said that bats produce an enormous amount of echolocation calls in an hour. And so we can be somewhat selective in our interpretation because there's generally so much data present on the landscape. So other things that we want to talk about for interpretation is when we challenge the software and we maybe change the species ID based on visual examination. There should always be some justification. You should be able to explain it to somebody and say, I did it because of this. And there are absolutely legitimate reasons to do that and to challenge that. They should just always be supported. You need to kind of make decisions based on the weight of evidence, and that's kind of what the MLE is trying to do is aggregate all that information and say, in overall, what does this picture tell me about what species are present? So if you're doing that with species ID, need to think about it from that weight of evidence. Watch out for red bats. Many reasons to watch out for red bats, but this one is red bats make echolocation calls that look like a bunch of different species. And the other thing is when you are doing the call analysis, it's always good to have an idea of what the structure looks like there. Is it maybe a little bit more cluttered? So you maybe expect a little more FM call structure to there. And then this is somebody was asking me about how I do identifications. So I used to get a lot of people to send me files and say, hey, can you verify that this is an Indiana bat or a red bat? And sometimes I could look at it and say, yeah, that's what that is. Sometimes I could say, no, it's not that. It's a red bat instead. And then there's this quote here that really describes it. Sometimes you just can't, there's no argument to be made to make the change, right? It said, well, yeah, I can see why it called it an Indiana bat. So you can't really change the ID. It's for the football reference, it's like a challenge in football. You can't always just confirm. Sometimes you just have to go with the way it was called. And that's important too. So that's the whirlwind discussion about the call analysis. And I just want to throw this one slide up here because it's something that, so Dave McNaughton and I have been tasked by OSD to do a lot of bat conservation and ecology efforts, one of which we've identified is trying to increase the amount of survey effort that's being done on installations, so we can address some data gaps. But as any of you know that's worked on installation, it's difficult to do bat surveys. You have to worry about configuring the hardware, trying to get software to do this, where you're going to store your data, all of this stuff. And so we understand there are these huge problems. We are actually trying to get past the idea of everyone using a computer, either their personal computer or an old computer that's just off network, and then doing stuff that way. We are, like I said, we have identified some ways we're trying to help this process, but I just want to say here that we've identified this as an obvious need, and the idea is to try and make it easier for natural resource folks themselves to be able to do the analysis and interpretation, rather than having to basically contract everything out. And so this project was funded by the Legacy program. And I think with that, I'll be happy to take any questions.
Thank you, Eric. We will now begin the Q&A portion of this presentation. Participants may use the raise hand function and wait to be called before unmuting and asking their question. Participants may also submit their questions to the chat. Back over to you, Eric. If I can use presenters' rights to ask the first question while folks enter questions in the chat. That chart that you showed earlier with the temporal variations of bat activity at West Point.
Yes.
What would explain such dramatic variations over, a couple months?
Yeah, so that's a good question. Part of the answer is we don't understand what the ecology of bats outside the summer maternity season as well. So if that were a migratory species like a silver-haired bat or a hoary bat, we might expect those two pulses to be just migration events. Maybe there's a cold front coming through and they just followed that down. And so that's why you saw that level of activity. But with a big brown bat that doesn't migrate very far, it actually is quite surprising to see peaking activity right after the young become volant, and then for them to more or less disappear from the landscape. So I wish I had a better answer to your question, but I think that's what's going on. Yes, Sean, you got a question?
Hey, Eric, thank you. And great presentation. I'm sad I missed last week, so I'll have to watch the recording. To build on what you just said in your answer to Daniel, for me, especially thinking about plants and other aspects of ecology, you want to monitor on a very regimented structure, especially speaking of plants, but it kind of sounds like there are a lot of variations or a lot of causes to the variations you may see in the data. So if I put out a logger for, say, 2 months, should I pay close attention to weather patterns and log those as well to look for correlations and plan accordingly for future monitoring? Or is it just so unknown it's not worth the effort?
No, I definitely don't want to give the impression that it's not worth the effort. Basically, we're at the point now with the hardware that's able to record for an extended period of time. And when I say extended, I mean very long term. We've got the analysis tools that we're able to have more confidence in their classifications, do that. It's really the time to do things even for longer periods of time. So you can come up with more or less permanent stations, and we've deployed these at some of our installations where the biologist has to go by every month or two, maybe to pull a card or check on the equipment or something like that, and you can get year-round data for basically a minimal amount of work. And that's the longer the data set, and the more data, more stations we have out, then we can start really answering some of those questions you mentioned. Until then, we're gonna, if it's just one detector at one site, it's gonna be very difficult because of all the variation that's out there. So hopefully that helped.
We have a question from Kathleen Smith in the chat. Kathleen says, great presentation. Have you found a way to differentiate between LABO and LASE search calls yet? If not, we would have the same challenges with LASE that we have with LABO, overlapping call characteristics with other species, correct?
Absolutely, that's the case. And so yeah, I think there's still some uncertainty about the ability to separate those two. And part of that, frankly, is there's still some uncertainty about how to separate them in the hand reliably. So yeah, that's a great point, that anything I said about LABO would apply to other Lazarus bats, basically. Whether it's even, we talk about Seminole, but we talk about Western red bats too. They would have potential overlapping with other species. And so you're right, it's not just an Eastern red bat problem, it's a genus problem. Good point. I need to include that in the next presentation I do.
If anyone has any other questions, feel free to enter those in the chat or use the raise hand function. We have another question from Kathleen Smith. If we want to get a bat monitoring program established on our USACE property, can we contact you for guidance on process, or is there another POC?
No, actually, yeah, you can contact me for sure. I, along with Dave McNaughton from the Navy, who I will volunteer for lots of things since he's on mute, are there to help. And so we are in the effort of developing some tools that may help in that establishing a program for sure. But yeah, definitely reach out. That's what we're here for. And that also applies to the military installations folks as well. So several of you know, although Seth, you can't ask us anything, Seth. Well, I don't know if I confused everyone, put them to sleep, or answered all their questions. So.
All right, Eric. Well, any last words you'd like to add to the presentation?
I would just say at this point, if you have questions that pop up or you didn't want to discuss them here, feel free to contact either Dave or myself. We're here to help.
Well, Eric, thank you very much for sharing your insight and experiences. This concludes today's presentation. Today's session will be recorded and then posted on the Natural Resources Denix website under the Resources tab. Thank you everyone for joining us, and have a great rest of your day.